Alright, let's do this problem about solvable and nilpotent groups. By the way, there is a football game going on and it's Halloween weekend, so there could be background noise, but it shouldn't be too bad. But yeah, so for this problem, so this is really good because we get to review the definitions of solvable and nilpotent groups, but we also see an example of why they're not the same thing. Alright, so what we want to do is we want to look at this. So we have these matrices here of the form A, B, D, where so A and D are non-zero complex numbers, and B is any complex number, and it can be zero. So let's see B, all such matrices where A and D are 1. So we're first going to prove that this is a commutator of C. I.e. the subgroup generated by things of the form alpha, beta, alpha inverse, beta inverse, where alpha and beta are both contained in B. So the commutator of B we want to prove is C. So let's take any two elements in B, like this. Then you use the typical like basic linear algebra, or even like pre-linear algebra. Like this is, I think you might even learn this in high school. But wherever you learn it, this is like the general formula for looking at inverses of a matrix. But why is this different? There's something... Oh yeah, no, it's fine. I just multiplied through here. But anyways, using this, we can write out alpha, beta inverse, beta inverse, and you do a whole bunch of stuff. It looks like this, then you multiply these two together, and then you get this. But look, we have ones here, and then we've got some complex number here, and so this is an element of C. And it holds for, so every element of this form is contained in C. And elements of this form generate the commutator of B, and so the commutator of B is contained in C. So that's one inclusion, but we want equality, so we want C to be contained in the commutator of B. So we want to find two elements alpha and beta such that alpha inverse, beta inverse is equal to any arbitrary element chosen in C, which will mean that we can realize any element of C as an element of the commutator of B. Alright, so take any gamma, just an element of C. I just wrote it like this so that I could fit it on here without having to write out a 2x2 matrix, because that when you're typing that up in a line of code, it would make this line look really like big. It's just a formatting thing, why I chose to write it like this. So now we do the same thing up here. We let A be minus 1, B 0, and C and D are both 1, and then E is x, and F is negative 2. I just did some fiddling with the coefficients to see what would work here to give us this form, to make basically what we want is this part of this formula up here for alpha inverse, beta inverse to be equal to x. And setting these constants gives you precisely this. So this is equal to this. We just computed that above. And then you plug in these things, you get x over 2 plus x over 2, so that's just x. And so this is our arbitrary element gamma. And so therefore gamma is contained in a generating set for dB, so any element of C is contained in a generating set for the commutator of B, and so C is contained in the commutator of B, and hence they're equal. Alright, so now what? We know that C is abelian. The complex numbers are abelian, obviously, and so then C is abelian, because if you look at C is just things of the form 1, 1x, and so if you take, come on, pen. Oh, I should click on the pen. If I want to do a pen, I should click on the pen option. Okay, there we go. Great, now I'll have to cut that part out. Alright, so now that I figured out how to select the pen, 1x, 0, 1, 1y, 0, 1. Well, what is this going to equal? We're going to get a 1 here, and then this we're going to get 1 times y plus x times 1, so this is going to be x plus y. this here we're going to get 0, and here we're going to get 1. Right, so C is basically just, C here, this C is basically just the complex numbers under addition, because all that happens here is when you take two elements and multiply them, the 1, 0, 1 part stays, and then you just take the two elements in the upper corner here and you add them together. So that's what happens in this group. So, yeah, so it's basically just addition, which is abelian. And so there, oh, I should hide the bottom there. And so C is abelian. We know the commutator subgroup of any abelian group is trivial. Right, because if you look at any element of the commutator subgroup, alpha, beta inverse, because of commutativity, you just you move the alpha inverse by next to each other, and same with the beta inverse, and the alphas and the betas cancel, you just get 1. So every element is 1, and so the commutator subgroup is a subgroup generated by 1, which is just 1. So it's a trivial subgroup. And so therefore, D2 of B, which is just the commutator of B, well, the commutator of B is C, as we just proved, so D squared B, or D2B, is the commutator of C, which we just proved is trivial. And that's what it means for the group B to be solvable. It means that you take D to some finite number and you get trivial. Alright, so now as for nilpotency, so let's take the commutator of B and C, and we want to prove that's equal to C. So take any element beta in B and gamma in C, and then you just do some math here, just some computations. It's not hard. You get this, and so this we see is an element of C, because we got the 1, 0, 1, and then just some complex number here. And so this holds for every element of the generating set, and so because it's generated by elements of this form, and so therefore the commutator of B and C is contained in C. For the reverse inclusion, we need to do the same thing as before. We just need to choose our constants here to make everything work, and let B equal 0 and alpha be 2C, or A be 2C, which we know is not going to be 0 since C was chosen here, and it's just it was chosen to be a non-zero complex number. So anyways, you just plug these values in, we get this, and then you get minus x plus 2x, which is just going to be x. And so you can, given any gamma in C, you just take beta inverse, where beta is 2C, 0, 0, C, and it doesn't matter what C is, you'll still recover gamma, and so then gamma is contained in the generating set for this, and so all of C is contained in there, and so we have equality. Okay, and then that pretty much finishes off nilpotency, because then we take C1 of B, well, C1 of B is just B, and then C2 of B is the commutator of B, which is C, and so then you just use induction here, because, well, wait a minute. Right, so after C, what we're going to do is we're going to take the C3 of B is going to be, we're going to have C3 of B is going to equal commutator of B and then C2 of B, which will equal B and commutator of B and C, which is C. And so we're going to get, so C2 of B is C, C3 of B is C, and then you could just see that in general, if you have any n greater than or equal to 3, such that this holds, then basically this is just this calculation over here, but you replace the 3 with the n. And then, of course, 2 becomes n minus 1, and it's the same thing. And so then by induction, C the n, B is C for every single n greater than or equal to 2. And C is not trivial, obviously. And so then there is no natural number n, remember natural numbers don't include 0 because I like analysis, such that this holds. And so therefore B is not a nilpotent group because c to the n never gets down to the trivial group. So then we found a group B which is solvable but not nilpotent. And this completes the proof.